Okay, hi everyone. Welcome to the seminar. Today we have Neil Barrie from the IBS in Korea. So Neil actually did his PhD right here in Sydney with Archil before moving to a postdoc position at the IPMU in Tokyo. And since then he's been a postdoc at IBS. So thank you, Neil, for coming and giving a seminar, and I'll hand it over to you. Thanks.
Thank you for the introduction, and thank you for the invitation. I'm happy to give a talk here. If I can't be there in person. So today I'm going to be talking about a paper that Cheng Han and Hitoshi Murayama and I put out recently on arXiv, so you can have a look there for some of the extra details on Affleck-Dine Leptogenesis from Higgs inflation. So the main motivation here is we wanted to consider a simple extension of the standard model, which is the introduction of triplet Higgs, and we wanted to see whether we can solve three main mysteries of the standard model of physics and cosmology, namely the setting up of the inflationary setting, the matter-antimatter asymmetry, and the neutrino masses. And we're going to see if we can just do this within this simple framework of just adding a triplet Higgs. So to discuss this, I'm going to firstly just introduce some of these main issues and how the triplet Higgs will address each one, bring it all together and discuss the model framework as a whole. Going to go through the Lagrangian and so on and show the equations of motion. And then I'll look at how the actual asymmetry is generated in this model, looking at the relation between the comparing the numerical and analytical results. And then bringing all of the results together, we'll look at the allowed parameter regions, considering constraints from inflation, phenomenological constraints, the LHC and so on, and also Baryon asymmetry constraints. And we'll see if there's much parameter space for which we can successfully do all three. And then conclude. So, as we all know, when we look out at the universe, we see that the universe is composed of predominantly matter and not antimatter. The asymmetry is quantified by the so-called asymmetry parameter, and it has this value from observation. In order to generate such an asymmetry, we require the satisfaction of the so-called Sakharov conditions in the early universe, assuming CPT invariance. Firstly, Baryon number violation. Obviously, if we start with a net zero or it's diluted from inflation, you need some source of Baryon number violation. You need C and CP violation, so some asymmetry between the reaction rates of these interactions, and then a period of non-equilibrium in which to accumulate this net Baryon number. Interestingly, the standard model can satisfy each of these conditions, but when you look at the predictions from how it satisfies each of these conditions, the resultant asymmetry parameter is orders of magnitude lower than that required to explain observation. So this is a key motivation for new physics beyond the standard model. And it has been used many times to motivate many models, many new models for baryogenesis. And the one that we're going to be particularly interested in here is the baryogenesis mechanism involving inducing angular motion in the phase of some complex scalar field, and this tends to be known as Affleck-Dine baryogenesis. So what we just imagine, we have some complex scalar phi, and it has some global U1 charge, some charge under the global U1 symmetry. And so this U1 symmetry could be lepton number, Baryon number, some combination thereof. If we write down the current and the associated charge density of this phi, it comes out in this form. And if we go into polar coordinates, so we pull apart our real scalar component and the complex phase, we find that the charge density is proportional to the time derivative of theta. Meaning that if we want to have some non-zero charge density associated with this phi, we require the generation of some theta dot, so some motion in this complex phase. Now, if you look at the actual equations of motion for n phi, so you calculate from the Lagrangian, what you find is that you get this term here, which if you want some non-trivial evolution of this n phi or theta dot, you require that the potential includes some term that explicitly breaks this associated U1 symmetry. So in order to generate some charge density, you require this. So this complex scalar field requires some breaking term. So this is how this mechanism, this is the main components of this mechanism, and this is embedded typically into inflation. So just to briefly look at the original iteration of Affleck-Dine baryogenesis. So when it was first proposed, they considered this supersymmetry context, and the reason for that being that you have many fermions, or the scalar superpartners of the fermions, that carry B and L. These scalars also have flat directions in their scalar potential. The other component is that we also have high dimensional B and L violation. So you have all the components for which you could induce some motion, angular motion, in the complex phase of these scalar partners. And in so doing, you would potentially generate a net B and L. And given that these superpartners have couplings to standard model particles, you can have it decay later on into subsequently decay into standard model fermions. So we want to consider something similar to this, but what we want to do is rather than worry about introducing all the SUSY particles and superpartners, we just want to introduce one complex scalar field, the triplet, the triplet Higgs. And you might ask, well, why would you introduce this? And so the key motivation for considering a triplet Higgs typically in the standard model is in the form of the type 2 Seesaw mechanism. So as we all know, the neutrinos have non-zero masses, and there's various mechanisms as well that people have considered to generate those masses. Typically, these are the so-called, there's a whole class of different Seesaw mechanisms, but the original one being introducing massive right-handed neutrinos. But what we want to consider here is the so-called type 2 Seesaw mechanism. And so what in this model, you have your usual standard model Higgs doublet, and then you introduce your triplet Higgs here, which is this delta. Now, when you introduce this term, you can then write down a Yukawa coupling with the lepton doublet given here. Now, the nice thing about this is that when delta gives a VEV, it gives mass to the neutrinos, but also through this, we can define that the delta itself is charged under the lepton number, which is our first ingredient. Is what we need is some complex scalar with a U1 charge, which is lepton number. And the other nice thing about this model is that you can then have couplings between the delta and the H that inherently violate lepton number. And the usual term, this is some high dimensional term which we're going to include, but is this cubic term where you have this mass dimension 1 coupling mu, and this is inherent in the type 2 Seesaw mechanism. So here is just a pictorial, things showing up, pictorial representation of how you generate the mass of the neutrino, and it's related to this coupling here as well as this coupling here. So as I said, we're going to introduce also this high dimensional term, which you could construct from this. Okay, so, it's not moving. Okay. Yeah, so this triplet Higgs, it has that, it introduces those sort of couplings and terms. As, of course, it has its own mass terms and quartic coupling, and there is also a portal coupling between the Higgs and the standard model Higgs and the triplet Higgs. So, as I was saying, these triplet has a VEV, a non-zero VEV, which is what generates the neutrino mass, and it is associated with the neutral component of the triplet, and it has this form, and so it's dependent upon that lepton violating coupling term and the delta mass. Now, this there is constrained by experiment from precision measurements of the T parameter, while we also have constraints if we want to generate the correct neutrino mass from requiring that the coupling, the Yukawa coupling, doesn't become non-perturbative at the Planck scale. Now, given that there's also the doubly charged component of this triplet and the singly charged, you can get quite interesting constraints on the delta itself. And at present, the searchers constrain the delta or the triplet Higgs mass to be greater than 800 GeV approximately. An interesting component of the type 2 Seesaw mechanism, so many of the Seesaw mechanisms, they try to tie in leptogenesis as well. Unfortunately, just the type 2 Seesaw model on its own can't successfully lead to leptogenesis. And in order to do so, you're required to introduce an additional triplet Higgs. So what we want to consider here is just requiring only the single triplet Higgs. So that's what we want to consider. And then also what we want to do is now tying into the third issue. So we've gone through leptogenesis, neutrino masses, inflation. We want this delta naught to also play a role during inflation. So as we all know, again, inflation is the period of rapid expansion in the very early universe that is able to explain many of the observational results that we've seen when looking out at the CMB and so on. So things like homogeneity, flatness, and primordial perturbation, the prediction of primordial perturbations, and it's generally accepted as part of standard cosmology. Typically, the way to induce a period of inflation is to have some scalar field slowly rolling down some very flat potential. Many models have been proposed. This is from the most recent Planck release, Planck data release, and the current constraints with various possible inflationary models. And so there's been many models, but there's also some degeneracy in predictions. The model that we want to consider here in particular is this so-called R-squared inflation or Starobinsky inflation. A very nice component of this is that its predictions lie well right within the current constraints, inflationary constraints. And so we want to consider a model like this. And an interesting feature of such Starobinsky inflation and R-squared inflationary models is that they can be induced by having just one scalar field non-minimally coupled to gravity. So one of the more interesting ways in which this was first considered is with the Higgs boson. So we have a scalar particle in the standard model. We had one that we knew should be there. And so why couldn't it be the inflaton was the thought. And so when they first looked into considering the Higgs and the standard model Higgs potential, it was found that it was difficult to make the inflationary predictions consistent with observation. And this is largely because the scalar potential was not flat enough over a long enough period of time. One intriguing way of flattening potential is to introduce a term like this into your Lagrangian, which is a non-minimal coupling to gravity. So what happens is that for large field values, this term begins to dominate, and you can get rather different behavior associated with the potential. And so this is considered a Jordan frame and Einstein frame. There's some discussion about the consistency of transferring between these two. But in any case, this is in the Jordan frame potential, where you would have the usual standard model potential. It's not flat enough, but when you go to the usual Einstein frame, the conformal transformation leads to this so-called Starobinsky-like potential here. And as you can see, for large values of chi, which is an Einstein field representation of the Higgs boson, this is effectively flat. And this mass scale, known as the Starobinsky mass scale, is dependent upon the different couplings of the model, so the quartic coupling and the non-minimal coupling, and has a value here. And so, yes, this is quite a nice model. The constraints are well fitted. The observational constraints are well fitted by it. There's some discussion about the effectiveness of this non-minimal coupling there. So now that I've gone through those three main problems and how the triplet Higgs is involved in each, bring it all together. So we're motivated by those three problems. All we want to do is add a triplet Higgs and see whether we can unify each of those into one nice simple solution. And how we're going to do this is that we're going to have some two-field Higgs inflation type model where we're going to have some combination of the standard model Higgs and the triplet Higgs playing the role of the inflaton. And the hope would be that this would lead to a Starobinsky-like inflationary setting, which is consistent with inflationary observations. Then we have this delta has lepton number violating interactions and has some lepton number charge through its Yukawa couplings. We want to see whether that lepton number phase can be given some non-zero value over the course of the inflationary epoch, leading to some net lepton number density being generated. And then subsequently that lepton number in the thermal plasma will survive and be redistributed from lepton number to Baryon number as in usual leptogenesis via sphalerons. The delta will take its vacuum excitation value, giving the neutrinos a mass, and then hopefully all these things will be consistent. And then who knows, maybe we might be able to find hints of the required triplet Higgs in colliders. So now I'll just take a drink. Okay, so here is the actual, so I've just laid out how the model is going to work. And so here is the Lagrangian and all the required terms. So we have our usual kinetic terms, and we've introduced our non-minimal coupling here. And I haven't written the Yukawa coupling, but we have our Yukawa coupling. And our potential has the following terms. Now, I've written here in just the unitary gauge for simplicity. You can look in the paper for the full form. But we have our mass terms, chordic terms, our portal term, and we have our two violating terms. I'll discuss later if anyone's interested. I've got it in the backup slides, but why we end up introducing this additional term and not rely on this cubic term. But I'll discuss a little bit why in what follows. In any case, so now that we want to look at the inflationary setting, to do this, we first reparameterize our fields with in the unitary gauge. We reparameterize our fields into their real scalar component and their complex phases. So here and here, the eta associated with the H is not going to be dynamical for us, so we don't need to actually worry about that. There's no violating terms, but the dynamics of our theta here will be non-trivial because we have the introduced violating terms, as I discussed at the beginning. Okay, so further we can reparameterize these real scalar components, and we want to define this angle alpha, defining the relation between, or the mixing between these two, and then we'll have some real scalar component phi. And so our non-minimal coupling can be redefined in regards to these mixing terms as follows. Okay, so doing all these reparameterizations, we arrive at our Jordan frame potential as follows, with just our simple non-minimal coupling term here, and our potential and kinetic terms. So our potential reduces as well to be quite simple. And as expected, we have a five-dimensional and cubic component here. Now, the interesting part about this two-field inflationary mechanism with both having non-minimal couplings is that you can define the inflationary trajectory along a fixed value of alpha. And so what you find is if you consider this potential with all the alpha components and with the rows, you find that defined by all the different input parameters of the model is this trajectory. And so which field dominates the inflationary setting is fixed by this ratio and is determined by all those couplings. So that's sort of important for our model because, so as I showed before, let me get back. We've introduced both possible ways in which you can have a 5-dimensional term. There's one which has 4 Higgs components and one that has only 2, while it has 3 delta components. Depending on which field dominates the inflationary setting more, whichever term will dominate, because that field will have larger field values. One can also see that the reason that we've introduced a non-minimal coupling for both of these fields is that because all of the lepton number violating fields contain both Higgses and deltas. So we need both fields to play some role so that they aren't massively suppressed, or these violating interactions do play a role during inflation. So that's an important point, and is why we consider this 2-field case. In any case, with this fixing of alpha, we basically now can define our inflaton as just this field phi. And so this is our Jordan frame inflaton. And so if we want to consider the inflationary predictions of this model, we need to go to the, well, we don't need to, but we will go to the Einstein frame. And so the Einstein frame transformation looks like the following in various different regimes, depending on the field values. So our chi is what we'll define as our Einstein frame field. And as you can see that for large field values of phi, you have this sort of relation, which ends up being exponential in chi, which is quite important. While during reheating, they related by square root or square. And then once you get after reheating and the field values become small, the definitions of the fields in the Einstein and Jordan frame coincide. And once again, this can be seen in the potential, the Einstein frame potential, and see how I said this exponential term. Well, that comes in here. This exponential behavior is important because it leads to the Starobinsky-like potential for large field values, while we end up getting an m squared phi squared type potential during reheating. And subsequently, again, we revert back to the usual quartic of the Stanimol potential. And as I said before, we have this Starobinsky mass, which is determined by lambda and xi. I should say, when I've written the potential here, I've sort of pulled all the different couplings together into mixtures here. If you want the full form of those, you can see them in the paper, but it's quite straightforward. Okay, so now that we've got our Einstein frame field of potential, we can then just go and calculate our equations of motion. And so we have our usual motion for a scalar field, but with this additional term here, which is just going to be just a friction term for chi. But we'll find that this term is, well, obviously the variation of chi with time is small during inflation, so this isn't too important. And also, we find that this theta dot is never large enough to cause any implications. So this just reduces to our usual inflationary setting, and we can just model that as such. While theta gets a somewhat more complicated looking dynamics here, where we have this chi-dependent friction term, which is unimportant during inflation because the time we were considering like slow roll parameters. But then we also have the lepton violating terms inducing a potential in theta. And these are phi dependent. I've written them here just for simplicity rather than putting them in terms of chi. But one should note, say we consider the large field values of phi, we end up getting this term becomes like 1 on phi, and so your cubic term is proportional to 1 on phi, while our phi-dimensional term is proportional to phi. As shown here, if you convert phi into a function of chi, it has an exponential-like dependence. And so here you'll have an inverse exponential, which means that this term is suppressed for large field values, while this term is enhanced for large field values. And so at the very beginning of inflation, we'll find that this term is more important than this term. Well, we sort of require this, but with this term only becoming important once field values become smaller. So yes, so here this is the equation of motion. So just pull everything together. So we have this Starobinsky-like potential. We're going to mainly focus on this dimension 5 term and take the cubic term to be suppressed relative to the dimension 5 term. We're going to assume some non-zero theta naught, but we're going to assume that the theta dot is 0. And we're going to consider this trajectory along which alpha is approximately constant. And throughout this, we're going to assume that the motion of theta does not affect the motion of chi, so that the inflationary trajectory is unchanged and just gives us the expected Starobinsky-like behavior. And then we can, from this, although I'm saying these are assumptions, we solve it numerically as well as analytically to find how these things evolve. Okay, so now that we've got all these pieces together, we can start actually looking at the predictions of this model. And so we're going to look at what sort of motion is induced in theta. So once again, I've written my equation of motion for theta here. And so what we're going to do is, as I already discussed, I said if we consider this inflationary setting, there's various assumptions we can make. So this phi goes away. So I should say this is just, I'm showing you the analytical. We solved it purely numerical in the plots we'll show, but I'm showing the analytical reasonings for why the behavior we get is what it is. In any case, so in the inflationary setting, this goes away, and then we can sort of define, just push all these things into this C inf, because we're assuming that during inflation, this is slowly varying. So we'd imagine this C inf doesn't vary too quickly. And then this comes to this rather complicated form when you look in terms of chi. But as I was saying before, what we find here is that we get this exponential enhancement for large chi values, while here you get an exponential suppression for chi values. So this helps push this term away during inflation and have this term be important. When I say it's important, it's still quite small. This C5, which I think should actually be lambda 5, is very small and also plate suppressed. So this is also not a large coupling like this 5-dimensional coupling. So anyway, simplifying, we get this, it's simply just ignoring this mu term for now, we get this rather simple form for C inf. So now we want to consider the very beginning of inflation. So we said the initial conditions are that there's no motion in theta, but we'll consider that there's some non-zero theta naught. So at this point in time, you can imagine that there's no friction term. It's just the potential is just whatever the potential slope is going to induce in terms of acceleration. And if we assume that this theta is approximately small, we can solve this very easily and derive what our motion would be expected to be. And as you can see, it has this term here, which is just saying it's a very simple equation, but it has exponential growth with time. And so what happens is that it quickly starts to roll down the slope. And you can see this here in this yellow line is like just an exponential, while the blue line is the numerical calculation. So what's happening is that at the very beginning, it starts to roll down its potential dominated evolution. And as the theta dot increases, we can no longer neglect the friction term. And so then the friction term becomes important. So this is how we can understand what happens at the beginning. And now we want to see what happens after this. So we have some theta dot start to be produced. Now what we find is that we enter this effective plateau period during the inflationary epoch and across the inflationary epoch, where the friction of the slope and the equilibrates with the slope of the potential. And so what happens is you end up achieving effectively a terminal velocity in this theta dot, which is approximately constant across the whole of inflation. So here, well, it varies by a factor of a half, but this is because the equilibrium condition changes in this C inf, because our chi value is changing across from the beginning to the end of inflation. And so you're going to have some variation, but it's only slight. and this gives a very good approximation to this terminal velocity definition gives a good explanation for what happens during this inflationary epoch. So
Sorry,
one
can I
thing
ask quickly.
Yeah.
Maybe I missed this. So, are you solving the equation motion for chi at the same time as theta, or?
So chi, you could just imagine like it's independent of the dynamics of theta. In the numerics, yes, we are solving them simultaneously. Yeah, that's what I was trying to say. Here I'm doing very simple things to try and show you how y it's doing what it's doing, but the numerics is a full simultaneous thing.
Okay, so and then this C inf is dependent on
yeah. So that exactly, yeah. I've got to be careful because I'm doing very simplistic things here, but it's actually this whole dynamics is very complicated, and that's one of the things that I was saying before, that we don't want the theta dot to affect the inflationary trajectory, right? Okay. So one thing that's nice is that this fixing of this terminal velocity here is not actually dependent on the initial chi, because it's just dependent upon the Hubble rate and this value of C int. And this is going to be, when this inflation ends, this C int is going to be the same no matter what the chi naught was at the beginning. So we're sort of, this type of evolution is sort of independent of the length of inflation. So we can sort of fix the length of inflation to be 50 to 60 epochs as required. Okay, so this is what happens over the inflationary epoch. And then we get the kind of more complicated part of the setting, which is during reheating, when we have this oscillatory behavior in phi. And because we have this oscillatory behavior in phi, or in chi and in phi, we have a rather more complicated dynamics of theta. So here is the equation of motion again. And so we can define that. So if you pretend this whole messy part isn't here for the beginning, this is the full numerical calculation. We have this evolution here, where the yellow is theta dot and the blue is chi. Right? Okay. Sorry, phi. So this is phi, and this is theta dot. So what we find is that when you get into this reheating regime, so it tracks this nice behavior the whole time, but when you get into this reheating regime, you end up getting it this large oscillation from phi being transferred into theta dot. And so here I've zoomed in to show the behavior. Now, what's interesting is there's two important periods of time here in this oscillation. One where if you look, they match this whole time. Is the peak of phi, and when phi dot equals 0, which once again, if you just to look here, when phi is at its maximum and this is 0, you could match up again with our approximate sort of terminal velocity type equation. While as phi goes to 0, our theta dot rapidly increases as well. And so if in that case, as this term goes away, this term becomes important, like this friction term associated with phi. And if you notice, this is just theta dot dot to phi dot on phi theta dot. And if you actually solve that equation, it comes out that your theta dot is effectively just a constant, and at those points. So, okay, this is getting a rather complicated explanation here. But what I'm trying to show here is that this is theta dot and phi dot independently, but what you find is when you put them together, you get an NL that is constant because of the way in which they relate to each other, which is this phi squared times theta dot. So as I was saying before, if you look at when the friction term alone dominates, so there's phi dot on phi dominates in the theta term, and you solve that equation, it basically comes as this. So that what theta dot we have is approximately, so if you consider it those maximums, is approximately whatever the maximum of the phi is divided by the phi at the max. and then multiplied by whatever the initial theta dot was. And so this theta dot star is what I was saying at the beginning of reheating, kind of. Is defined by this terminal velocity. This is not a great explanation, but I hope that makes sense. But the interesting thing is that if it has this kind of behavior across each oscillation, so the main loss in theta dot just comes from Hubble friction, and in that decreasing. If you multiply this by R5 squared, which you expect from the lepton number density, you end up just getting a constant, or effective constant, ignoring Hubble friction. And what do we see when we actually just calculate this directly? We see a constant during this reheating epoch. So that all this variation that's induced in theta dot through phi cancels out in the actual calculation of the charge density. So this NL, what we've done is, this is the numerical calculation. So across the whole, from the beginning of inflation to the end of reheating, well, when reheating ends, we can sort of choose. We have this behavior, this exponential behavior that I first showed. We've got this flatness, and then this initial drop comes because when Hubble friction starts and the maximum value of chi drops quite a lot, like there's this period in which you lose a lot of energy in phi. So that's mainly where this drop comes from. But then it enters this regime when it settles into this oscillation where the theta dot approaches effective constant value. And this value you can easily calculate from this fixing for any given reheating temperature. So putting all these approximations together, we can write down an approximation here and match that and see how well it fits with the numerical simulation. And so we give him one example here, and I cut off the exponential part because this doesn't really model that exponential part very well, but it models the behavior very well and then enters this constant behavior as well. And if you want to consider the ratio, comparing these values, they're very good at the beginning of inflation, but this changes a little bit because there's some change in theta naught and there's some change in H, which I don't really take into account in this approximation. So what we can imagine is that as you change this value, this ratio typically is between like a factor of 2 correct with the final asymmetry, this approximate value. And this gives us a way of doing it without having to run a numerical simulation every time for every combination of values. But then we find that this approximation is very good. And so now, I just took the time. Now that we've got this final value for the lepton number density, we can start considering the final lepton number density at the end of reheating, and then the subsequent baryon asymmetry. So as I showed here, it's dependent on this phi max. Well, the phi max at the end of the reheating epoch, you can sort of directly consider the energy density that's at the maximum in the scalar field with some instantaneous reheating. So we assume that at some point it is instantaneously converts all that scalar potential energy to the thermal bath, and then we can get an approximate value for what the final lepton number density is. And nicely, what happens is because we have this relation with phi, that any dependence on the reheating temperature cancels out when you consider the actual final lepton number density to entropy ratio, because it has the same dependence on the Hubble rate. And so when you put all these together and you consider usual Scalar redistribution, we find that our final asymmetry is given by this value here, and it's just dependent quite simply on these various parameters. And so this C5 tilde incorporates both these violating terms, and as I was saying before, you have to consider what that value takes is going to be dependent on which of these two fields dominates, and this is also the same for the chi, because once again we have chi H and chi delta, and whichever non-minimal coupling comes through here will be dependent on which dominates, although of course we could have some very special case where they both share equal weight. In any case, so one of the assumptions that we made is this dimension 5 term doesn't affect inflation. And if you just simply take this result, you can get a maximum for the Baryon number density ratio, and it's just given here. And so it looks like it's very easy for us to get enough asymmetry, even in the case where we cause problems with the inflationary setting, which we don't want to do. So it seems like it's quite easy to get successful baryogenesis. All right. Okay. So now I've gone through. I've shown all how we get the Baryon number, and we've motivated all the things. Now we're going to look at all the different constraints that we can apply on our model and the model parameters, and then we're going to see what region is allowed by current observational constraints and experiments. So this messy slide, I'm not sure, I'm approaching the 40-minute mark, I think, so I won't do this too much time. But so as I just said before, one of the first constraints is we want to require that this is approximately 1, the E to B on E to B observed ratio. So from that, we can get a constraint immediately on lambda 5 and xi and theta naught. There is one thing I didn't mention is, of course, we're assuming that, we require that the lepton number that we generate survives in the thermal plasma. So because we've introduced these lepton violating interactions, it's possible that you could have washout. So you need to consider the different interactions, namely lepton-lepton delta and Higgs to delta, which is this lepton violating interaction. And require that the parameters and the couplings are such that at no point is this interaction in thermal equilibrium. By requiring this, you automatically require this one. So we mainly rely on this constraint here, and this is given here. I'll show you the plot. You can see which parameters are excluded by this washout region, but there's a large region in which we don't have problems with washout. One other thing to consider is a particular feature of cue ball of Affleck-Dine mechanisms is the formation of cue balls, and there's the potential that if they're stable, that they can basically capture all your lepton number or Baryon number, or whatever it is, and it'll be stuck as dark matter, and you won't actually see it as an asymmetry. In our case, because of the way that we're considering the flattening of the potential with the non-minimal couplings, we don't end up having any stable cue ball formation. So this isn't a problem for us either. Now, as before, I said that this inflationary epoch is unaffected by those 5-dimensional terms. So the chi effectively runs inflation on its own and will lead to Starobinsky-like predictions for the NS and R, which are consistent with observation. The number of E-folds is fixed by the initial value of chi. And we have this requirement to get the correct Starobinsky mass scale, which is a requirement on the quartic coupling combination and the non-minimal coupling combination. So we can use this constraint. One other thing to consider is that in models with these complex scalar fields, during reheating, the angular degree of freedom can lead to unitarity violation. But this is one of the things I was saying, that large non-minimal couplings can be an issue. But as long as you require that the quartic couplings and the non-minimal couplings satisfy this relation, you can avoid this problem. And so we require that. Another issue is the potential for isocurvature perturbations, which for us puts in a constraint on what the initial theta naught can be, which is related to the number of E-folds. And this ends up being like 0.01 or 0.001 in that sort of range, depending on the number of E-folds you choose. And as I said before, we've got this constraint on our lambda 5 coupling so that it doesn't affect inflation. So this we can combine into our constraints as well. And this is how I got the constraint on the upper bound constraint on the matter-antimatter asymmetry. Okay, and then so we've got the inflationary constraints, the baryogenesis constraints, and then we also have just the constraints on the triplet Higgs itself at LHC and its VEV. And then we also have constraints on the neutrinos in order to get the correct neutrino masses which also places constraints on these, but on the various couplings. And we required that the neutrino-Yukawa coupling doesn't become non-perturbative. Okay, so I've gone through, these are the many constraints that we have to contest with in trying to pull all these three things together. And what we find is quite nicely is that there's quite a large parameter space in which we can satisfy all these constraints. So here this is just one particular set of input parameters. In this case, the delta ends up dominating the, somewhat dominating the inflationary setting, and that's why this alpha is 0.022. I should say this isn't a free parameter, it's fixed by these various parameters. And so if we assume these parameters, you can assume other choices, but some of these are fairly generic sort of things. We get this large region here where we can have successful inflation, leptogenesis, and also produce the neutrino masses for given Yukawa couplings here. And what's of interest is this, I guess, and here's the washout region. And what's quite interesting is that we have quite a large region in the TeV range, which is still open, and that could be probed at future colliders. One thing to note, I have got here that the mu term dominates as a constraint. We've throughout the discussion, I sort of assumed that this mu term is not dominant over the lambda 5 term during inflation and reheating. And part of the reason is that if the term is very large, not only it can begin to affect the inflationary epoch, and it can also causes significant oscillation and loss of predictability in the net lepton number asymmetry. So although it may be possible to get successful leptogenesis through this model, it's not something that we can easily model analytically or even numerically. Like, it becomes very complicated. So we sort of settled for this nice region that we can easily calculate for. In any case, to conclude, what we're considering is just this fairly simple extension of the standard model based on triplet Higgs. And in doing so, we've been able to use that triplet Higgs to set up an inflationary setting in concert with the standard model Higgs boson. The inflationary observations are well within current constraints and are very good. The leptogenesis is fairly easy to achieve in this scenario, which is different from if you just consider the usual triplet Higgs scenario with in the type 2 Seesaw mechanism. The triplet Higgs also, when it takes its VEV, can give us the neutrino masses. So we can solve all these things with just the triplet Higgs. And when we bring all those constraints together, we find that there's still a large region of parameter space, and it's a parameter space that could be probed at future colliders, which is all seems very interesting and well motivated. Thank you. Hope you enjoyed the talk. It made sense.
Thank you. Yeah, thank you. That was very interesting and very clear. Can we? Do you have any questions from the audience? Just go ahead and unmute yourself if you do. No one's raising their hand. Maybe I can go first. So, well, I mean, I think the most immediate question for me is what are the future collider signatures? I mean, you have this constraint. I think it was on M delta of 800 GeV. I think is that the sort of constraint that you're talking about?
Yeah, so the current constraint, yeah, so they're just from the current LHC data. You have this 800 GeV constraint, and that mainly comes from, I think, searching for the doubly charged component of the triplet, and I think that's looking for I think that's typically in the 4 photon channel. There's various different signatures. It depends on. Okay, so it's somewhat complicated because it's dependent upon what this size of this mu is relative to the mass, and there's different regions of parameter space have different sort of signatures that dominate. I think in our case, it would be like I think it's a 4 lepton case for the types of mu's that we consider, because we consider fairly small mu mu values, which like 10 to the negative 3, 10 to the negative 2. And so this lepton number violating interaction is somewhat suppressed. So it sort of changes what types of signatures you would see. I would imagine if we considered some future collider like the 100 TeV proton-proton collider or something, maybe we would be able to probe this range. I think that's what we'd be hoping for.
So can I interpret this plot as being bounded from the left by these collider's constraints?
Yes.
Okay.
I would say, yes.
Yeah,
We
okay.
probably should have, We probably should have extended it slightly.
Yeah, okay.
Yeah.
So this is a closed. This white region is more or less closed. I guess you could.
Yeah, so I guess you could imagine that this would keep going down to even smaller mu's until it hits that wall. There is, so what I was trying to say before is that we've selected values here, which I would say are somewhat motivated, like in terms of like the Higgs couplings and these, and with respect to the constraints. But you can alter these quite a lot. Like if you make these so they're not the same, make this lambda bigger or smaller and so on, you can alter these a little bit, like this range, but you inevitably always get this sort of, the mu value might change slightly by an order of magnitude or so, but you can always pretty much get some region which is in this TeV, 10 TeV range. Yeah.
What about like neutrino mass measurements? Would they help you at all?
So the neutrino mass measurements, so I guess, so so the neutrino mass is dependent upon this Yukawa coupling and this mu. So just knowing the neutrino mass itself and the mass of the delta, so just knowing that itself might not tell us a lot. Like it wouldn't be a bad thing to know. Like it would help a little bit, but it wouldn't fix everything. We'd probably need another measurement to help to really pin this down, right? Yeah, but I guess it would help, but we need a little bit more.
Do we have any? Anyone else want to jump in? Tobias?
Maybe a follow-up question. So you said that you can kind of reproduce the overall neutrino mass scale correctly. I might have missed that, but can you make any further predictions with regards to whatever neutrino mass ordering, for example, or can you predict any of the mixing angles or some of these things in these models in the neutrino sector?
Like so in our case, it's quite generic in that it doesn't require anything on those, like on how those mixings would be or what those couplings are. We've only constrained the largest Yukawa coupling, right? So although you could introduce those sort of constraints and things on those mixings, in our case, I don't think it really has any implications on the predictions for either the inflation or leptogenesis, right? But I would imagine you could embed certain textures or structures into how this generates the masses into this scenario. Yeah.
Okay.
It would be nice if it did that. Yeah.
So I think one thing I missed, a minor point, was the number of e-folds of inflation. So I think you're generally consistent with just Starobinsky predictions, but there was a sort of range of, as I remember in the plot you showed earlier.
Oh yeah. So this range, So I think it's 50 and 60 e-folds. Yeah. Here we go. Yeah, 50, 60. Yeah. So that's why I was saying So you have this 50 or 60 e-folds, which then puts a constraint on your chi-naught, which I have I think I've got the paper here. I don't know if you can see on my camera. I have it's well, if you want to look at the paper, it's equation S6, but it's like I didn't include it. It's that one.
Okay. Yeah. So this is prescribed by whatever chi-naught is. Okay.
Yeah. So you put constraints on some initial chi-naught, right? And so that is somewhat important for us, but not really. Like it's not really important, but I guess you could say it's somewhat important when looking at like how you suppress this mu term to the 5-dimensional term at the high scale, and also, but the main implication of the number of e-folds is from the isocurvature perturbations, because we set it at 50 or 60, then you end up getting like whatever it is here, like I think it's 0.0 0.02 to 0.003 or something like that.
And I guess like future like cosmological probes might, I mean, because this R that predict that Stravinsky inflation predicts is so small. I mean, I guess that sort of
that's one of the nice and the good and the bad things about the Stravinsky model is it's sort of I don't even think the current Stravinsky predictions will be found by like Lightbird and that, even though their predictions are so precise. I think it's still below that. But if say Lightbird finds nothing, then like Stravinsky model would be considered probably quite nice.
Yeah, I guess it rises further to the top of the crowd.
Yeah.
It's not completely ruled out. Okay, so we're coming up on an hour. Do we have any final questions that anyone wants to?
There you go. That's fine.
Maybe I'll ask one final one. It was just a sort of generic question about. I mean, you do a sort of a numerical and an analytic approach.
Yep.
And I think you had a plot where you were, I think it was the ratio of the numerical solution, the analytic solution, and you get some like order 1 discrepancy. So I think you mentioned you're using this as a sort of argument to proceed with the analytic calculation when you look kind of exploring the parameter space. Does this discrepancy hold across the parameter space, or did you check it first?
Yeah, so I, at the time, I think I didn't say it, but yeah, so that if you compare different parameters and so on, if you look at this final region, it tends to vary within like maximum like a factor of 3.
Yeah. Okay.
Or a factor of 2. So it's fairly robust. And the main reason you get discrepancies is not because this epoch doesn't act like this, which it does. The reason is because here, in this period, because I fixed theta naught in my approximation, there is actually sometimes some variation in theta naught across inflation. And so that can then change your sine theta. And then that's mainly where the change comes from. So it works very well. But this behavior is pretty consistent. I will just show you, I did have in the backup slide what happens if you introduce a large mu. So this is the plots of what happens as you increase the factor of mu. So this is that behavior. So this is with a somewhat small mu, and you get some oscillation in the lepton number density. And as you increase mu, that oscillation gets larger until a point where when you violate interaction, it just becomes chaos. Like it's just oscillating back and forth between positive and negative values of the lepton number. So and as it gets larger, this oscillation dynamics dominates even more. And so this is why we don't want our mu sort of having an impact. And then if you go even further, it starts effective inflation as well. So you start out where mu doesn't matter, and then as it gets more and more, you get this weird bump in mu. So sort of bump in the NL. And anyway, this is just a side note. But
why do you have to have this mu parameter? This was the cubic term, right? The h squared delta.
Yeah, that's the cubic term, right? So it should be there. What size it is somewhat of a free parameter. Like I guess you would expect its scale to be somewhat related to the other couplings and the mass scale of delta, right? Yeah. And and of course, in choosing a small mu, we also choose a very small lambda 5 because we're assuming that high dimensional term sort of comes from there. So
yeah. Great. So I think we're out of time, so I'll stop recording.